Hello class, these are our notes for 5-4. Today we're looking at exponential functions. We're going to be differentiating and integrating. So I think first we need a little review of what an exponential function is. So exponents and logs are related. And if we want to look at natural exponential function, we're talking about e. So if we think about the function y equals e to the x power, this is really the exponential form of the function, the natural log of y equals x. And so these are equivalent. And I think a lot of times we're good at going from log form to exponent form, but maybe not from exponent form to log form. So think about how we would change something into exponential form. We would think about this little e here, and we would say, well, e to the x power is equal to y, right? So that's how we would be changing that back. The way I think about changing from exponent form to log form is if my base raised to my power is e, then that's my base here, which means I have a natural log. And logs are always equal to my exponent, so my x has to go over here, and then the only thing left is y. So that's kind of how I look at changing from exponent form to log form. But this is just review, right? This is just stuff we should already know about exponent form and log form and how they're related. So this is just review stuff here. And I am going to go back and write that again. This is y equals e to the x. This one, again, because it's e, I'm going to say natural log because that's base e. And then it's of y and it's equal to the exponent. So those are the two that are equivalent. So this is just review. What we're more focused on right now in this chapter as of like yesterday was inverse functions. So if we have a function f of x equals the natural log of x, then its inverse is going to be e to the x power. And then I can kind of show you that with the graph here too. So e to the x power looks something like this. And it's crossing through, okay, so this would be e to the x power. And then if I think about my natural log, looks more like this. Okay, so they are both monotonic. We always think about cubic functions, but there's lots of other kinds of monotonic functions. They're both one-to-one. We have an inverse. So that's kind of like our thing that we need to be worried about today. Just kind of thinking about how those two work. And then remember that, and this is what we're going to use for solving. Remember that. And these three different ideas are kind of unrelated, and that's okay. It's just all the pieces of information that we need to know for the math that we're doing today. So do remember that if I take a natural log of e to the x power, it's just equal to x because natural log and e are inverses. And if I have e to the natural log x power, that's also just going to equal x because e and natural log are inverses. So these are just like I said, different things that we should remember about exponential and of course log functions to be able to do our math today. So the first two examples are actually kind of a throwback to Algebra 2 and then even pre-calc we solved equations like this. So the way we approach this is we said, well, my x that I'm solving for is in my exponent, and I need to be able to get at that exponent. I need the exponent to go away. And so we know that logs and exponents are inverses. So if we log both sides, and because it's e as my base, I want to use a natural log because that's base e. So I'm going to go ahead and take a natural log on both sides. And then we knew that natural log and e were inverses. And so we were just left with x plus 1. And on the other side, we had natural log 7. And then to solve for x, all we would do is subtract 1 on both sides. And we're just leaving it this way. This is not a day where we're worried about decimals. The second one, I have a natural log of 2x plus 3 equals 5. Well, the stuff I need, my x is inside that natural log, so how do I get a natural log to go away? And that's when I would raise both sides as a power of e. So it's called exponentiating. A lot of times we call it raisins because we're raising both sides to a power. So we're going to exponentiate both sides, and we're going to use e as our base. And that's because if I raise e to a power that's a natural log. Like again, we have inverses, we're left with 2x minus 3. And then I'm just going to go through and finish solving here. And again, leaving x as an expression is just fine. We don't want to go through and work that out. These are not the only way to solve these two problems. You might have also seen a trick before where you just change back and forth between log form and exponent form, but this is the method that I think works best for most students and just kind of makes the most sense when we look and talk about inverse operations. So now we're going to actually look at the calculus part of today, and that's taking the derivative of e to x. And there's lots of really great math memes about this. You should definitely look some of them up, because when I take the derivative of e to the x power, it's actually just e to the x power. If I have e to the u power, and this is of course in terms of x, so like u is some kind of function, this would be e to the u times u prime, or e to the u times du dx, right? So it's like you have to do chain rule, and you have to make sure you take the derivative of that function as well. I usually just memorize, like I said, this first one, and then I just remember, but there's also a chain rule. Right? I don't like to memorize two different things, and I feel like the second one's a little more complicated. So the way I would use this is, well, I'm taking my derivative of e to the 2x minus 1 power, so I would just rewrite what I have there, e to the 2x minus 1 power, and then times, and then chain rule, we have to do our derivative of the exponent, 2x minus 1, that's just a 2. So this is going to be 2e to the 2x minus 1 power. Same thing on the next one. I would just write this as e to the negative 3 over x power times, and then I'd have to figure out the derivative of that. For this one, I might kind of go off over here on the side and think about that derivative. Let's see. This is negative 3 times x to the negative 1 power. So if I take my derivative, negative 1 times negative 3 is 3. And now I have a negative 2 power. So y prime is 3 over x squared. Okay. Now I can go back and I can finish this problem. So I have e to the negative 3 over x power times my derivative of the exponent, and now I know what that is, right? It's right here. So I'm just going to write times 3 over x squared. And it might look prettier if I wrote 3 to the negative 3 over x power, 3 times e to the negative 3 over x power divided by x squared. And maybe I should do something with that negative exponent. I don't know. We'll just leave it. It's kind of ugly. We're back to looking at extrema, which I think is really good. I like it that we keep cycling through and looking at these problems. So let's remember our step. Our steps are to take the derivative, make it equal to 0, do a first derivative chart. So we need to do all of those steps. So let's go ahead and find f prime of x. And I do need to remember when I look at f of x here that I have two different functions multiplied. I have x times e to the x power. So let's go ahead and find our derivative. So first I would write down my first function, x, and take my derivative of the second. Well, that's just going to be e to the x power plus, now I would write down my second function and take my derivative of the first. So f prime of x is going to be x e to the x plus e to the x. Okay, now I want to figure out where it's equal to 0 and then also where it's undefined. Well, it's not going to be undefined at all. I don't have to worry about that. So all I do have to worry about is finding where my f prime of x equals 0. This is going to be my critical numbers. And so let's go ahead and set that equal to 0. And we'll factor out e to the x power. And e to the x can never be 0. Remember, if we're taking a number and raising it to a power, we can't get negatives, we can't get 0, right? Even if I take e and I raise it to like the negative 100th power, all it does is make a really tiny fraction. So that's not going to have a solution for that part of my equation. So I'm just going to cross that part out. And my second part has a solution of negative 1. So now I'm going to make a first derivative chart. So I'm going to label this f prime. Negative 1 is what we're curious about. So I'm going to go ahead and check 10 and negative 10 in my first derivative. This is a first derivative chart. So let's think about e to the 10th power times 10 plus 1. Well, e to the 10th power is a big positive number. 10 plus 1 is also positive. Positive times positive, positive. Let's think about e to the negative 10th power. Well, that's going to be positive, right? It's just a fraction. But then we'd have negative 10 plus 1. So positive times negative is negative. So it looks like we have a minimum at x equals negative 1, but we want to actually figure out what the minimum is. So we'll go back to our original function and find f of negative 1. That's going to be negative 1 times e to the negative 1 power, or negative 1 over e to the first, so just negative 1 over e. So we have a minimum of negative 1 over e at x equals negative 1. All right, cool. I like that we're going through these kinds of problems again every time we get a new derivative or integral. All right, on the back. So just like when we take a derivative of e to the x, we get e to the x. When we integrate e to the x, we get e to the x. But of course, we always have to add the constant, so e to the x plus c. And then this one would be e to the u plus c. So we still might have to do u substitution. So let's take a look at A. A says we are integrating e to the 3x plus 1 power. So if we think about, because it's not just x for my exponent, right? I have an expression there. So I'm going to let u go ahead and equal that expression. So my derivative of u, my du, is going to be 3 dx. And so in order to have this e to the u du kind of thing, right, I need to have that 3 dx in there. So let's write e to the 3x plus 1. And then we have times the 3 dx. So this part's my du. This part's my e to the u power. And then if I am multiplying a 3 in here, I need to have a 1/3 as well. Right? 1/3 times 3 gives us back the dx. So now when I integrate, all that's going to happen, remember, is we're going to get e to the u plus c. So that means my answer is going to be e to the 3x plus 1 power plus c. Oh, don't forget about the 1/3. So if you need to, you are fine. You could go back and take a derivative and make sure that this works. Remember, there's always ways to check your answer. On the next one, I want to do the same thing. I want to let u equal my exponent. And then my derivative of u, my du, would be negative 2x dx. So this 5's kind of in the way. I'm going to stick that in front. And I would want to start with negative x squared. Okay, that's going to be like my e to the u power thing. And then I need a du. So the x is already in here because I can't just go ahead and multiply integrals by x. I can multiply them by constants, right? But I can't multiply by x. And the constants, it's like if I multiply by a 2, I also have to multiply by a 1/2. But I can't do that with variables. So I need the du to be in there. I need there to be a negative 2x dx. But that means that I have multiplied by a negative 2, right? That's the difference between this original one. Here I just had an x. Here I have a negative 2x, right? So, because I've already taken the 5 out. So I need to have a 1/2 in front as well. So I'm going to make this, oh, and a negative. So I'm going to make this now a negative 5/2 instead. And that's going to fix this negative 2 over here. All right? So now I can go ahead and integrate. When I integrate e to the u du, it's just e to the u. So I'm going to have negative 5/2 e to the negative x squared power plus c. It's really good for us to be doing u substitution again. This next one looks kind of weird. I'm going to go ahead and let u be my exponent again, though. That kind of makes sense for what we're doing. So let's go ahead and let u equal 1 over x. Which is x to the negative first power. When I take my derivative, it's going to be negative x to the negative 2 power dx, which is negative 1 over x squared dx. So I can see where I could use that x squared now, but I do need a negative sign in there. So I'm going to rewrite this. I'm going to write my e to the 1 over x power times, and then I have a 1 over x squared dx. But again, I need a negative. So if I want this to be a negative here, I need to multiply a negative in front. And now I have my e to the u power again, and I have my du again. So when I integrate, I'm just going to get negative e to the u power, so negative e to the 1 over x plus c. So on the next one, we're going to do the same trick again. We're going to let u equal the exponent. So u equals cosine x. Derivative of cosine is a negative sine x, which I actually have in here, dx. So this is going to work out really well. So I'm going to write e to the cosine x power times sine x dx. But of course, again, I need to have a negative with my sign. So I'm going to multiply another negative in front, because two negatives when I multiply would just make a positive. And now I have my e to the u power, and I have my du. So my answer is going to be negative e to the cosine x power plus c. So we're going to look at a few definite integrals as well. I think it's always good for us to be practicing these, but maybe not as many, right? Because we need a lot of help with integration. These take longer because we've got to substitute some values at the end, but they're still good for us to have to figure out. So let's go ahead and do this. So let's think about u equaling the exponent, which is a negative x. There we go. So my du is negative dx. So all I really have to do here is put in a negative. So let's go ahead and do that. So I'm going to put a negative in front. And then I have a negative dx. So now when I integrate, it's just going to be a negative. And basically just that e to the u power, right? So negative e to the negative x. And then we're going to evaluate it from 0 to 1. And I'm going to just leave that negative sign outside, do all my evaluating, and then distribute that negative. So this is going to be negative e to the negative 1 power minus e to the 0 power. So let's see. Negative of e to the negative 1 power is 1 over e minus 1. And then let's go ahead and multiply that negative. Negative 1 over e plus 1. So 1 minus 1 over e, I could leave it that way. I could get a common denominator. I could multiply the first one by e over e and make it e minus 1 over e. That would be okay as well. So lots of different ways to write out this answer. I kind of like either this one or this one if we want one fraction. Again, we're not grabbing the calculator today. Don't worry about it. This next one looks a lot more complicated. I don't think we can't use our exponent as our u substitution. It's just not going to work. So instead, I'm going to look at how my denominator is a whole expression, and I'm going to let u equal my 1 plus e to the x power. So if I take a derivative of that, well, the derivative of the 1 is just 0. Derivative of e to the x is e to the x, and then dx. So what I actually have here when I make my u substitution, actually let's separate it out first. Let's say 0 to 1, and let's say 1 over 1 plus e to the x times e to the x dx. And then I am going to go ahead and do the u substitution on this one. So when I do a u substitution, my bounds are going to change, so I'm not going to fill those in yet, but I'm going to have a 1 over u, and then I'm going to have a du. So this is back to natural logs at the beginning of the unit. So if I'm going to make a u substitution, I need to also go through and I need to change my bounds. My bounds are x values. I need them to be u values. So let's remember this is going to be something guaranteed you're going to have to do on the AP test. It's going to be a multiple choice question. So let's look at our lower bound, and it's 0. And remember that's an x value. So if x is 0, I want to change it to a u value. Well, u equals 1 plus e to the x power. That's what we did up here, right? Up here we wrote this equation, u equals 1 plus e to the x power. That's what I'm using to convert. So instead of the x, I am using a 0. So 1 plus e to the 0 power is 1 plus 1, which is just 2. So my new lower bound is going to be 2. Now I have to convert my upper bound, 1. So that's going to be 1 plus e to the first power, which is just 1 plus e, or e plus 1. I kind of like it better as e plus 1. Okay, so now I'm going to go ahead and integrate. When I integrate 1 over u, that's a natural log. Remember, I can't use power rule when I have, this is basically a negative first power because negative 1 plus 1 makes a 0 power. It doesn't even work. So this is my natural log. So I'm going to integrate this as natural log u, and then we need to evaluate it from 2 to e plus 1. So natural log of the quantity e plus 1 minus natural log 2. And that is a perfectly acceptable answer. We're going to leave our work that way. So for our last problem, this one looks a little bit more complicated. So let's think about u being this part. I mean, the part that looks inside is the part that's inside my cosine function, right? The e to the x power. So let's that be our u. If our u is e to the x, our du is e to the x dx. So let's think about how basically what we've got here is we've got a cosine e to the x and then times an e to the x dx, right? So we really just have cosine of u and then we have a du. So in order to do this though, I would need to once again change my bounds. So my x equals negative 1. When I convert that, it's going to be u equals e to the negative 1 power, which is 1 over e. And then my upper bound here would be x equals 0. Well, that would be u equals e to the 0 power, which is just 1. So my upper bound is going to be 1. So when I go ahead and integrate this, when I integrate cosine, I get sine. So now I have sine u from 1 over e to 1. And so we're going to have the sine of 1 minus the sine of 1 over e. Or maybe just e to the negative 1 power would have been better there. And I'm not going to worry about evaluating that again. So this is a great answer. All right, so I like that we had a little review here of u substitution. I do think e to the x power is pretty easy to work with as far as derivatives and integrals go. And hopefully we had kind of a good refresher of exponential properties and log properties as well. All right, if you have any questions, please make sure you ask.